Hello and welcome to this section of the Calculus 1 Derivative Tutor. This section we're going to continue working problems with related rates, expanding our skills and just building our confidence in how to handle these problems. So in this section we'll work a few more problems with related rates, going from the problem statement all the way through to the answer. The general technique is going to be exactly the same as what we've done in the last section, so don't worry too much about it. It's just that, just like with any other type of problem in algebra or geometry or whatever, there's sort of the easier problems that you can sort of see how to solve a little bit clearer, and then there's the medium problems, and then there's the harder problems. So as you go, there's a progression, and these problems are going to be a little bit more involved. So they'll still follow the same procedure, so don't forget that. It's just that as we begin to do it, we'll see that we're going to have to solve for a few more things before we can actually get all the way to the final answer. So definitely don't throw away what we've learned before, expand on what we've done before. That's all we're doing here. So the first problem says we have a cone, like an ice cream cone, and this cone is 6 meters in height. This cone is 6 meters in height and has a radius on the base of 2 meters. And so it's flipped upside down like an ice cream cone, 2 meters, 6 meters high, okay? Water is entering and flowing into this cone, and it rises at a rate of 1/2 meter per second inside the cone as it rises up. How fast is the water being poured in when the water has a depth of 2 meters? When the water has a depth of 2 meters. So there's a lot of things here to understand to make sure we quite get. There's a little bit of interpretation that you'll get as you work more of these problems to know how to tackle it, but the first thing that we always do is draw a picture. So let's do that right now. So we have a cone, right? So let's go ahead and draw ourselves a cone, first step. So here we have a cone, right? Draw it like this. Do your best to kind of draw it as a sort of a nicely shaped cone. And the height of this cone, so we'll just kind of do some curly braces to help us out, 6 meters, all right? And then the radius of this cone goes from the middle out to the edge, and I'm just going to draw a little arrow here, is 2 meters. And by the way, it's good not to clutter up your diagram. See, if you try to draw 2 meters and the word, the 2M, inside of here, it's going to clutter up your diagram. So draw some arrows. Get your labeling away from your drawing. It's a good habit to get into anyway. This is pretty simple, but certainly it can help you. All right, now, since we have colored markers, we'll have some water in blue. And so here's like a faucet, and so here's water coming down here, and water is kind of coming into the cone, and we'll just draw like a little level inside of here, right? So water is going in, and as you might think, if the cone is empty, the water goes all the way to the bottom, and then as time goes on, the water level rises all the way up until we get to the top of the cone. So what we're told is water enters the cone at 1/2 and rises at a rate of 1/2 meter per second. Okay, right there, when you see a speed of any kind or something per second, you need to think, well, that's a derivative of something. So put that at the back of your head. How fast is the water being poured in when the water has a depth of 2 meters? So eventually this water is going to have a depth of 2 meters, right? So it's 6 meters tall, so somewhere around here is going to be 2 meters. At that moment, we're interested in something to do with the water. So let's just kind of take it one step at a time. What do we know? We know that dH dt is 1/2. Because it's meters per second. Now, what am I talking about h? What we're going to do here is construct a new diagram. Original drawing with all the labeling on there. Let's go ahead and draw another version of the cone. This version is not going to have the labeling of the numbers. This version is going to have the variables. So what we're going to do and say, okay, the water level is going to be going up over time as time goes on. At any given moment in time, the water is going to have a depth. That depth, let's call it h. Right? You have to make some labeling. We talked about that in the last section. As you get into the harder and harder, quote, harder and harder related rate problems, you're going to need to associate your own variables with your own diagram. And so that when you write an equation that governs that guy and you start taking derivatives, it'll be all self-consistent with what you've written down. So a lot of times they're not going to tell you the water depth is h. dH dt is 1/2. Now go solve the problem. They're not going to tell you that. They're just going to say, look, the water's going in at this rate. You figure it out. So that's what we're doing. You have to put some numbers here. So at any given moment in time, the height of the water level is h. Now the total height of the cone is a fixed 6 meters, so this was the first diagram we drew, but the water level height itself is h. And at any given moment of time, I'm going to draw it here in a different color to make it a little bit clear. At any given moment of time, the radius of this sort of where the water level is to the edge of the cone, we're going to call r. So you see what we've done is that when you have a cone like this, right, a cone shape, and water goes in, what you're doing is the water itself kind of like forms another cone within the cone you have. So no matter what time you choose to look at this guy, it's going to get larger and larger, but it's going to form a cone of water inside of the large cone you have. I mean, that's just common sense. If you have a glass of water, or a glass, I should say, just a tall glass, start pouring water in, well, the water level is going to rise. It's going to form a column of water or a cylinder of water as it goes up that glass, right? Same thing here. We're just forming a cone of water as we get higher and higher. And we're saying that the height of this cone of water is h, the radius of this cone of water is r. Why are we doing that? Because when we read the problem again, water enters the cone, rises at a rate of 1/2 meter per second. Well, if we label this as h, then what we're given in the problem is dh dt. The rate of change of the height with respect to time is 1/2, and that's meters per second. And that comes straight from the problem statement, 1/2 meter per second. That in your mind should mean derivative. When something is a rate of change of, in this case, position per unit time, that is the rate of change of this distance per unit time, dh dt, 1/2 meter per second. So what we have to do now is read the rest of the problem and figure out what we are being asked. So we've gotten the 1/2 meter per second rate of change of the height of this water. Next part is, how fast is the water being poured in when the water has a depth of 2 meters? Now here's where you get into a little bit of interpretation. And like I told you, when you do enough of these problems, you'll realize what they're trying to get you to realize that you need to solve for. So when you see something that says, how fast is the water being poured in? Or how fast is the water poured in? You might think what they're asking about is how fast is the water coming out of the spigot, but that doesn't really make sense because the problem sort of implies that you turn the water on, it's coming out at a constant rate, coming out of that spigot. So it doesn't make sense to be solving for that because, I mean, then the problem would have no meaning. I mean, the water's coming out at the same rate all the time. What you really need to do is dig deeper into the information they've given you. We know it's a cone, right? We know the radius and the height of the cone. That's a pretty huge indicator that we're going to be dealing with the volume of something in this cone because we're given dimensions of a cone. We're talking about the water level going up into this cone. We're talking about water that's inside the cone. That's a volume. So we're going to be talking about volume, right? So if you think about it in the context of volume, right, then if I look at this water that's in here, this is at any given moment of time, this is some volume V of water, right? 2 seconds later, the water level is higher. It's a slightly larger amount of volume, you call it V, of volume of water inside this cone. 3 seconds after that, the cone of water is even higher. So the volume of water is even higher in there. Now, since the cone is small at the bottom and then larger as you get to the top, then the rate of change of that volume of water as it rises inside of this cone is going to be changing. It's not going to be a constant rate of change of volume increasing inside that cone because the cone is physically larger up here. So I guess what I'm trying to say is when you look at the bottom of the cone, you start putting the water in, the water is going to be rising quite rapidly near the bottom. But as the volume of water increases inside this thing, the rate of change or the speed at which the height of this guy is increasing up here is going to slow down lower and lower because you're basically, that volume of that cone is getting larger and larger as it goes up. So when you read this, and you say you see how fast is the water being poured in, you shouldn't think about how fast the water is coming out of the faucet. What they're really asking you is what is the rate of change of the volume of water inside of this cone. That's what they mean by how much water is being poured in. Is like you have the water in there, the water level's rising. What's the rate of change of the volume of that water inside the cone? That's really what they're after. So in terms of calculus, right, if we look at this volume V here, right? So let's say at any given time we have a volume V of water inside of this guy here. Then what we're really after, what we're really being asked is, what is dV dt equals question mark at a depth of 2 meters, at a height of 2 meters, right? So since we've got everything labeled, we're in good shape because we start off here, the water level goes up. Once the depth of this water gets to 2 meters, at that exact moment, how fast is the volume of this water increasing as we go in there, right? So we have everything we need because we know it's a cone. We can write an equation of the volume of a cone. We can take the derivative of that. That's going to give us dv dt because it has the volume of the cone. And then we're going to try to plug in what we know into the other side to try to solve for dv dt. That's our roadmap. It's the same roadmap we used in the previous problems. Try to find an equation, take the derivative of that equation, and then go with it. So that's a lot of talking, but these related rate problems require a lot of talking because you really need to make sure you understand what it is you're doing. So the volume of a cone, if you look back in a geometry book or your calculus book, 1/2, or 1/3 I should say, pi r squared h. And this is why we labeled it as such, right? Because 1/3 is just a constant, pi is a constant, r squared h. Now when we say v cone, what we're really talking about is the volume of this little cone of water inside of here. That's what we're after, because that's what's changing. The volume of the giant cone here isn't changing at all. What we're really looking at is how fast is this volume of this water changing as we pour the water in. So when I say V cone, I'm talking about the volume of this water element down here at the bottom. All right? So ultimately, what we want to do is take the derivative of this guy, right? And on the left, we're going to get dv dt. And on the right, we're going to have some other derivatives, and then we're going to try to plug in what we know to get the answer. But when you start thinking about it a little bit more, there's a little bit of a problem because the problem is written. And here is sort of, this isn't really a harder problem. It's just that there's a little more thinking involved than maybe the previous problems we've done. Previous problems, we'd have just taken the derivative, plugged in some stuff, got the answer, not too big of a deal. In this case, if I take the derivative of the left, I'll get dv dt. Over here, I've got r's and I've got h's. So I've got like a crazy product rule here. It's going to make this derivative quite large, and I'm going to end up with a dh dt. That's cool because I know what dh dt is. I'm also going to end up eventually with a dr dt. If I do implicit differentiation, I'm going to have 2r dr dt. It's going to be a long term, but I'm going to have dr dt. Now, I'm not given dr dt. I mean, it makes sense that the rate of change of this radius is changing because as the volume of water gets larger, this radius is getting bigger and bigger. So it is going to change, but I don't really know what that is easily. All right, so what you need to do is look at what other information do I have in the problem to help me simplify this before I take this derivative. And if I look back, I haven't used any of these dimensions of this cone at all. So I start poking on that and I start seeing if there's anything that I can learn from that. Right? Well, if you think about it, let me just sort of redraw the cone down here. Right? Little cone here. Well, this is 6 meters, and this radius here, r, is 2 meters. So if I think about it for a second, then what this really tells me is that the height of this cone, if you look at these two cones here, basically, since this water cone is inside of the big cone, the angle and the shape of these cones are basically the same. So it's like I have a similar cones going on right here. The cone of water and the outer cone are basically the same cone. One is just scaled differently with respect to another. So if I look at this guy with the variables I'm interested in, I can take a ratio and say, look at this, h over r. This ratio of h to this radius r is exactly the same as the radius of this height over here, 6 to this radius 2. These are equivalent because the ratios are equivalent. Since I've got this water inside of this cone, the cones are exactly the same shape. It's just they're different sizes. So the ratio of h to r is the same as the ratio of 6 to 2 because they're basically the same shape cone with the same sidewall angle there. So if I do that, first this doesn't look like it's really a big deal at all, but if you really look at it, this is 3. So what you have is h over r is equal to 3. All right, and then if you move the r over here, you'll have h is equal to 3r. And if you solve for r is going to be equal to h over 3. R is going to be equal to h over 3. Now, why does this matter? Because what you found is that because this cone is a nice shape of a cone that's sort of a constant thing, the radius of this water really is what you found. The radius of this water is always going to be a multiple, or it's going to be h divided by 3. Always. It's going to be fixed. No matter if the cone of water is this big or the cone of water is this big or this big or this big, the radius is defined in terms of the height because it's a nice fixed cone. So if I take this radius and I stick it right in here, what I'm going to get as a result is going to be v is equal to 1/3 pi What did I say R was? R is h over 3. So I have h over 3 squared h. Now look at what I have now. I have the volume of this cone of water that I'm interested in, but it doesn't have any r's anywhere in here, only h's, only the height. So when I end up taking the derivative and doing all the math, I'm going to have a dv dt, and eventually once I do the calculus, I'm going to have a dh dt, but that's all I need. That's all I need because I know those pieces of information. And I sort of get around the fact that I don't know much about the radius because of the way the problem is really set up. So when I go down here and keep solving, v is equal to 1/3 pi. It's going to be h squared over 9 times h, right? And so when you continue simplifying this, what you're going to have here, 9 times 3 is 27, so what you'll have is pi over 27. That's pi over 9 times 3 is 27, and you'll have h cubed, So this is really what the volume is equal to. So this is what I really have. Now, I need to obviously take a derivative because I want to know dv dt, and I already know what dh dt is. So let's take the derivative with respect to time implicitly. On the left, I'm going to have dv dt. This is exactly like we've done in the previous problems. On the right, this constant stays out in front, so I'll have pi over 27. And then on the inside, I have to take the derivative of this h cubed. So I'm going to have 3h squared, but I can't stop there. I have to multiply by dh dt because I don't know how this height changes with respect to time. So this is sort of the chain rule business we've been doing for all of these implicit differentiation problems. So now I have dv dt is equal to. Now I have a 3 here and a 27 on the bottom, so I'm going to have a pi over 9. It's just simplifying this guy here. And then I'm going to have an h squared, and then I'm going to have a dh dt. Now I step back at my problem and I look and I see how close am I? Well, what I'm solving for is the rate of change of volume of water as a function of time when the height of the water is 2 meters. So I look at my equation and I see how close am I to what I'm trying to find. I'm interested in the rate of change of the volume of this little segment of water as a function of time. That's what I'm trying to hunt for. I know that I want to look at that when the height is 2 meters, which I know, and I want to know, well, I'm already given that dh dt, the rate of change of the height of the water, is 1/2. So I just plug this information in, and so dh, or I should say dv dt, is equal to pi over 9, and h is equal to 2 meters, and dh dt is equal to 1/2, and this is squared right here. So what I'm going to have is pi over 9, this is 4, this is 1/2. So dv dt is equal to. So what I'm going to have here, 4 divided by 2 is 2. So the 2 is just going to stay on the top, 2 pi over 9 dv dt. Now look at my units. As the rate of change of volume as a function of time. So volume on the top, meters cubed over, what is the time I'm talking about here? It's per second. When you look back at the problem statement, the water was coming in at 1/2 meter per second. So the unit of length is meter, so meters cubed. Unit of time is second. This is a funky looking crazy number, but you can put it in your calculator. 2 times 3.14 divided by 9, that'll give you a decimal. That is how many cubic meters per second is increasing of water inside of this cone at exactly the moment of time when the depth of this water is 2 meters. So let me just do a brief summary of it just to make sure we all follow along. So we have this cone of water, this cone here. Water is coming in. The surface level of the water is increasing at a rate of 1/2 meter per second. I'm trying to find out how fast the volume of this water is changing, or is increasing, when the depth of it is 2 meters. So I come in here and write the volume of the cone, but I realize if I start to take this derivative, I'm going to get stuck. Now, in real life, you might actually take that derivative and then you realize you're stuck, and then you go and kind of go backtrack a little bit and take another path. But I'm saving you a little bit of the pain here, because if you do a chain rule and a product rule on this, you're going to get dr dt, and I don't easily know what dr dt is. So I realize that these are two cones. One is the outer cone that have fixed dimensions that were given to me. The cone of water does change in size, but the ratio of h to r is always the same. H to r, the ratio is the same as 6:2 because it's inside of this cone. So I figure out that the radius of this cone of water is always going to be the height of the cone of water over 3, and I plug it into my volume of the cone formula. So what I get down when I do the math here is the volume of this cone of water is equal to something only in terms of h. I take the derivative, right, which I simplify, and I get down to the point where the dv dt is equal to some function of h and dh dt, which both of these things I know. I plug them in, I get the answer. So you see it's a little bit more complicated than in the previous problems, not because it's a crazy method or anything, it's just that sometimes you have to, once you get ready to take this derivative, sometimes you have to look at it and figure out, do I know everything that's going to need to be put into this thing? And sometimes you take the derivative and you realize you don't. Sometimes ahead of time you realize you don't. But either way, there's always going to be some information given to you in the problem to circumvent any lack of information you might have to put into there. So you might have to reach out a little bit and figure this out. Okay. The next question is a really interesting question. It has to do with a lighthouse, right, offshore. So the lighthouse is sort of like in the water on like an island or something. So we have a beacon on a lighthouse. It's 1 kilometer from the shoreline. And it revolves, this light revolves around at 10 pi radians per minute. So it's an angular rate, 10 pi radians per minute. Don't forget there's 2 pi radians in a whole circle. So this is 2 pi radians, or she said 10 pi radians every single minute. What is the speed of the beam as it sweeps across the shoreline and lights up the sand 2 kilometers from the lighthouse? 2 kilometers from the lighthouse. So you really have to do a little bit of thinking on how to set this thing up. Well, first of all, you have, and we'll draw a picture in a minute, but you have to think about it for a second. You've got a lighthouse offshore. So I'm the lighthouse, you guys are on the shoreline, right? So I'm a distance, it says right here, I'm 1 kilometer from the shore. That means straight line distance. So I'm 1 kilometer away from you, straight away, straight perpendicular to the shoreline is 1 kilometer. Now I'm revolving my light at 10 pi radians per minute. So if you think about it, the light is sweeping over here, and then it sweeps directly to you, straight away from me, which is 1 kilometer away, and then it sweeps the other way. Well, if you think about it, if you could like get in a helicopter and look at the shoreline as the light does this, the speed of this beam as it goes along the shoreline is going to change. Because yeah, the speed of the light is constant, but here I'm shooting it really far away and I've got a long slant angle, so it's going to be kind of like, it's going to be sweeping through that distance sort of faster. So it's going to kind of come in here and kind of slow down, then go faster, and then as it gets over there, it's going to come in here faster, and then it's going to slow down a little bit and go faster. So it's going to change a little bit as it goes round and round, and that's just because of the fact that once we get over here, in the same amount of time, this light beam is sweeping across a longer slant distance on the shoreline than it is when I'm directly ahead of you here. So it's going to change the speed of light. The speed of light's not changing, but the speed that this beam is sweeping along the sand is going to change as you go along the lighthouse. So just keep that in mind. So what we want to know is, what is the speed of the beam as it sweeps across the sand 2 kilometers from the lighthouse? So if the light is only 1 kilometer away, then what am I talking about when I say that I'm sweeping across the sand when I'm 2 kilometers away? Well, it just means I want to know what's the speed of the beam maybe over here. 2 kilometers from the sand, a slant angle, a slant distance of 2 kilometers away. What's the speed of the light over, sweeping across the sand over there? So I hope I've tried to illustrate what I'm talking about here, but it's still very important to draw a picture. So here's our lighthouse. Not a very good picture of a lighthouse, but there it is. Okay, and what I'm trying to say here is that the distance from this lighthouse to the sand, which is over here, right, is 1 kilometer. That's given in the problem, all right? Now, in the problem, it also says, what is the speed of the beam as it sweeps across the shore as it lights up the sand 2 kilometers away from the lighthouse? So if this is 1 kilometer, what am I talking about? What I'm trying to say is, maybe over here, this distance here is 2 kilometers. So the lighthouse is spinning around the beam like this. It's kind of going like this. So here's 1 kilometer, here's 2 kilometers, you know, here, the slant angle over here, maybe 5 kilometers. Then it goes out around the water again, the water's over here, and then it hits the shoreline over here, back to 1 kilometer. So the speed of this beam as it sweeps across the sand over here is going to change because of the geometry of what's going on here. We talked about that. So I'm interested in the speed at this exact point, right? I'm interested in the speed at this exact point. So we'll get into that in a little bit here. But if you think about the geometry here, this is going to form some angle. That's going to be important later on. And in our discussion here. So this is a picture of sort of the geometry with the numbers. Let's draw another picture. It's sometimes helpful to draw two pictures. Let's draw another picture with some variables, because in these related rate problems, we're always going to be dealing with variables. So we're going to have some angle theta, but more importantly, we know that when we look at this guy, the beacon on the lighthouse revolves at 10 pi radians per minute. What does that tell you? 10 pi radians per minute. When you see something per something, you should immediately think derivative. So this is, how would we label it? d theta dt. We know what this is. It's the rate of change of the angle of this light beam, and it's 10 pi radians per minute. So this is something that we're given, right? Now this vertical distance here is not going to change ever, so we're still going to label this 1 kilometer. But this distance here, this distance right here, we're going to go ahead and call this guy x. Because, you see, in this picture, I'm just sort of drawing a snapshot in time at the moment of interest with the labels that we have. And here I can go ahead and draw it again if I want to go ahead and put 2 kilometers here. But ultimately, what I've really got going on here is this distance is r. I'm sorry, this distance is x, and let's go ahead and label this distance r. Because as the light beam sweeps around, this distance x is going to change. It's going to get bigger and smaller like this, and this distance r is going to constantly change as well. This is what we're going to use to sort of construct our equation that we're going to end up taking the derivative of to actually plug in some of this information. So ultimately, when you look at this problem, what are we trying to solve for? We're given this. What are we trying to solve for? It says, what is the speed of the beam as it sweeps across the sand, right? Speed of the beam. Well, that should be dx dt. So what I'm trying to find is dx dt is equal to something, and I'll say when r, whoops, this should be when r is equal to 2 kilometers. And that's really in math what we're trying to find here. So dx dt, right, whenever the radius is equal to 2 kilometers, because at any other time, the r is going to be different, the beam is going to be over here, everything's going to be different. That's not what I care about. I only care about the speed of the beam when the radius is 2 kilometers like that. So sometimes it's better to draw two pictures. It's really up to you. You could put everything on this picture if you want to. Sometimes I like to draw the picture as given to me exactly from the book first, just putting labels in with numbers from what's given in the book. And then I like to draw another picture where I can put my own labeling in. Because notice, it never tells you to label this x, and it never tells you to label this r. These are variables that I'm inventing because I know that I'm going to need to use some kind of variables to write some kind of equation to do this here. So the next step is, what equation do you think you would use that you would end up taking the derivative of to find this problem? Well, I know d theta dt, right? And I'm looking for dx dt. So I know that whatever equation I use should involve theta and it should involve x. Right now, your first thought might be, well, this is a right triangle, so I'm going to use Pythagorean theorem. Well, you might be able to do that. You might be able to solve this problem this way. The problem is, if you do that, it'll be 1 squared plus x squared is equal to r squared. There's no theta in there. I'm not saying you can't solve the problem that way. You might be able to. But my first thought when I look at this is, well, I know some information about the angle. I know I'm trying to find the information about the x, so I should try to involve the angle in my equation so that I can take the derivative and get d theta dt and plug in a number for it. So what can you construct from trigonometry to do that? Well, there's lots of different ways, but the one that jumped out to me was r times the sine of theta is equal to x. R times the sine of theta projected gives you x. Now, this is the way I write it. You might not see it that way. You might need to tilt your head to the side to sort of see the right triangle like this. You could see sine of theta is opposite over hypotenuse. Sine of theta is opposite over hypotenuse. And when you back solve for that, you'll see that r sine theta is equal to x. It's exactly the same thing. So this is really the definition of the sine, is really all you're doing. Why do we want to do that? You might be reluctant to do that. Well, I don't want to introduce a sine here. That's going to make it super complicated. But I'm telling you, if you go down the other road, you might hit some additional roadblocks. If you start this direction, then at least you know you're going to be dealing with theta and x, and we'll deal with r as we go along here and see if we can figure out a way to get rid of that. So we look at this guy, we want to take a derivative of both sides and see where we end up. So let's go ahead and take the derivative of this guy. on both sides of the equal sign with respect to time. So here I have two guys multiplied together. So I go first times the derivative of the second plus the second times the derivative of the first. So starting here I have r. Inside here, derivative of sine is cosine theta. But I can't stop there. I have to go d theta dt. Okay? Because I don't know how theta changes with respect to time. That's how I do my implicit differentiation. So first times the derivative of the second plus the second sine of theta times the derivative of the first. The derivative of r is just simply 1, and then I can't stop there. I have to go dr dt. So that is first times the derivative of the second term plus the second times the derivative of the first. On the right-hand side, take the derivative of this with respect to time. I'm just going to get dx dt. So this is sort of the equation that I've constructed for my related rate problem. Now I look and I try to see, can I plug in information that I know from up here and solve for what I want? So I have my equation here that I'm going to end up using to solve this problem. And the first thing I need to do is look at everything in here and see if I already have enough information to plug it in here and solve for what I want. So what I'm trying to solve for is this, dx dt. So that's okay, that's what I'm trying to find, all right? And I'm also know what d theta dt, that's given to me, right? I also know what r is, actually, because r is a constant 2 meters. I mean, in fact, with 2 kilometers. We said that we're trying to find this when the radius, the slant height is there. So we actually, if we wanted to go and label it, we really know what this is. We know what this is. We don't know this, but we are trying to solve for it, so that's okay. So we know quite a few terms in this equation already. It's just that there's some that we really don't know. One of them we don't know. We don't know what dr dt is, and we don't know what cosine theta is, and we don't know what sine theta is. But in fact, those are some things that you can actually find from the rest of the information given to you. So let's first go with a slightly harder thing to find. Let's figure out what dr dt is. So we wrote this equation in terms of a sine, but in fact, let's draw a little break here. Let's say that we have a right triangle here, so we want to ultimately figure out what dr dt is, right? So let's go ahead and write Pythagorean theorem. 1 squared plus x squared is r squared. 1 squared plus x squared is equal to r squared. Why are we going to do that? Because I want to be able to put in dr dt. If I take the derivative of both sides, I'm going to get a dr dt. So let's do that. The derivative of a constant is 0, so I'll put a 0 here. The derivative of this is 2x dx dt. So 2x times the derivative of the variable with respect to time. On the right-hand side, 2r dr dt. All right? Now look at what I've done here. Doesn't look like much, but the 2's cancel. If I solve for dr dt, then what I have is dr dt is equal to x over here over r, and I still have dx dt. So what I have found is something quite nice, actually. If I take this, and what I'm going to do here in just a second is put it inside of here, then I'm going to basically eliminate dr dt from this equation entirely, and I'm doing that because I'm using additional information that I'm given, which is they told me that I'm 1 kilometer away, which lets me use the Pythagorean theorem. If you don't have that information, you can't do anything else with the problem. So let's go ahead and put that in there and see where it takes us. So let's go ahead and do that right now. So let's rewrite. We'll have r cosine theta times d theta dt, all right, plus sine of theta. All right, now dr dt, I'm going to go ahead and substitute in x over r, and then I'm going to have x over r dx dt, and on the right-hand side, I'm going to have dx dt. So it all becomes a numbers game to try to go ahead and use the information that you have to eliminate things from this that you don't know, and so that we finally end up with an equation that you can plug in information into and solve for dx dt. So it may not look like we've made a lot of progress, but we really have, because we've eliminated dr dt. Now we have dx dt here and here. We can combine those terms later. We do, in fact, know what r is. R is just the distance right here, the slant distance, so this is a number, this is 2. This is basically going to be 2. dx dt is what I'm trying to find. d theta dt is a number that I know. The only other thing that I really need to know in here is I need to know what this angle theta is, which I can find from the geometry up here, and I also want to know what x is, what this distance x along the sand is, which I can find from the geometry there. So let me go ahead and do that right now. Let me first of all start with rewriting this equation over here, just so we're all on the same page. So what I'm going to have is r cosine of theta times d theta dt, okay, plus sine of theta x over r dx dt is equal to dx dt. So really, there's two things that I really want to know. The first is I want to know what this distance x is right here. So I'm going to go ahead and just going to draw a little line here. I'm going to say need x. So the way I'm going to find that is I'm going to look at this guy and I'm going to try to figure out, or I should say I'm going to look at this guy, because this is also x right here. How am I going to find x? Well, if you think about it, this is Pythagorean theorem. 1 squared plus x squared is equal to 2 squared. So 1 squared plus x squared is equal to 2 squared, because 2 is the hypotenuse. So 1 plus x squared is equal to 4. So when I scoot this over here, x squared is equal to 3, and then x is going to equal to square root of 3. So I have an answer for that. X is equal to square root of 3. So let me go ahead and sort of circle this, because we're going to use this later. And let's see how much closer I am. I know what r is, that's 2. I know what d theta dt is, that's given to me in the problem. I know what x is now, that's square root of 3. I know what r is, that's 2. This is what I'm trying to solve for. So I have everything in this equation ready to solve, except I don't know what cosine theta is and I don't know what sine theta is. But I can also find that information from here. I'm given a right triangle. I'm given 2 sides of the right triangle. I can certainly find the sine and the cosine, so I just need to do that. All right, so what I'm going to do is, if you look at it, if you think about it, the cosine of this angle, if you kind of tilt your head sideways if it helps you, the cosine of this angle is going to be the adjacent side, which is 1, over the hypotenuse, which is 2. So if you tilt your head sideways, cosine of theta is adjacent over hypotenuse. So cosine of theta is equal to adjacent over hypotenuse. So that's 1/2, okay? So if you then figure out what is theta, if you look back to trigonometry, then cosine of theta is 1/2, then theta is going to be pi over 3, or 60 degrees if it helps you to think of it in terms of that. So now I'm all set, and I know it's kind of been a real pain, but we're going to go back through it to make sure that you completely understand. But for now, let's just go ahead and solve the problem, show you where we end up, and then you'll be able to see. The r is the slant distance, which is 2 kilometers. That's given to me in the problem. Okay, that's 2. Cosine theta, that's the next term I need. Well, I already know what cosine theta is. That's equal to 1/2. So I'm going to put 1/2 here. All right. D theta dt is given to me in the problem. It's 10 pi. Right? It's just a number in radians per minute. Plus sine of this angle, pi over 3. So for now, just keep it as sine of pi over 3. We'll come back in the next step and evaluate that as a number. That's the angle I'm given at the moment in time I care about. All right, times x, which is this distance here, x, I just calculated as the square root of 3. Square root of 3 over. R is the slant distance. R is equal to 2. That was given to me in the problem, so that's just a number. Dx dt, I don't know, is equal to dx dt. I don't know. But when you look back at it, there are numbers basically for everything else, so I can definitely solve this guy. Okay, so the 1/2 is going to go out with the 1/2. And so what I'm going to be left with is 10 pi plus, what is the sine of pi over 3, or if it helps you, the sine of 60 degrees? That is going to be square root of 3 over 2 also. Square root of 3 over 2. That's what this is. Multiplied again by square root of 3 over 2 times dx dt is equal to dx dt. So we'll just keep on simplifying. And so what we'll have here is 10 pi is equal to square root of 3 times the square root of 3 is 3. 3/4, because 2 times 2 is 4, dx dt is equal to dx dt. Okay, so now what we're going to do is move this entire dx dt term over to the other side. So I'm going to have 10 pi equal. I have 1 dx dt minus 3/4 dx dt, so I'm going to be left with 1/4 dx dt. And then finally dx dt, just multiply by 4 to get it over here. It'll be 40 pi. And that is the answer, but what units am I dealing with? The unit of distance is in kilometers. We've been talking about kilometers offshore. The unit of time that we've been talking about is in terms of minutes. Kilometers per minute. Do we get the units back from where we started from? The beacon is 1 kilometer offshore. It revolves at a rate of 10 pi radians per minute. So that's where we come from. So if you convert this to a decimal, then what you're basically saying is that beam of light is sweeping across the sand along the x direction here like this at a rate of 40 pi, whatever that comes down to in terms of a decimal, kilometers per minute. So you see what I'm saying? The process is the same. You draw a picture, you identify your variables, you write an equation, you take a derivative. The only difference that made this a little bit harder than some of the previous problems was that once we got down to our equation, we didn't quite have enough information to plug in. We had to go back to the problem to pull more information out and to stick it in there. So I want to briefly go over that again. So we have a lighthouse. It's 1 kilometer away from the sand. We're interested at the point in time when it sweeps out where the beam is 2 kilometers away. So we would label this distance r, and we label this distance x. The reason we do this is because we have to write an equation expressing these in terms of derivatives. We're trying to find dx dt at the moment when r is 2. We're given d theta dt, the rate of angular rate that the light is spinning around in a circle in radians per minute. So we look for an equation that we can, there might be different ways to solve this problem, but the way I did it was to try to find an equation that relates theta to x, because those are things that I know and that I'm trying to solve. So I say r sine theta, r times sine theta is equal to x, and that comes straight from triangle geometry. So I get that and I take the derivative. This is a product, so it has to be first times derivative of the second plus the second times the derivative of the first. So I get this and I look and I say, well, it's great, but I don't know everything. I don't know dr dt, I don't know sine theta, I don't know cosine theta. So I'm kind of stuck. But the good news is I do know r, I do know this, and I do know, well, I don't know this yet, but I'm solving for it, so that's okay. So I need to work on finding this additional information. I go back to my triangle and I realize since it's just a straight triangle, I can say 1 squared plus x squared is r squared. I get this, and since I want to eliminate dr dt, I take the derivative of both sides of this equation. You can take a derivative of both sides of an equation just like you can, add 3 to both sides of an equation, or divide by square root of 2, or multiply by 5. I mean, you can do whatever you want to an equation as long as you do it to both sides. Here I'm taking the derivative of both sides of this equation only because I want to get this. So I take it implicitly, I solve for dr dt, and I get this. This is nice because when I put it back in here, my equation changes from this to this. So it's a little bit better because I don't have any dr dt anymore. I have this dx dt in 2 different places, which is okay because I'm going to end up solving for that. The only thing that introduced that's a little bit crummy is that I don't know what x is equal to. So I go over here, I rewrite the equation, and I start hunting for x. And I realize that x is very simple to find because the geometry is given 2 distances. I can easily find a number for x at this moment in time. So I do that using Pythagorean theorem. I figure out that x is the square root of 3. Okay, cool. The only other thing I need is the angle, and again I go back and I say, well, I want to know this angle, but I have 2 sides. So I just go ahead and do the cosine and I get the angle. Ultimately, all I do then is plug in 2 for the radius. The 1/2 comes because that's cosine of theta. This was given to me in the problem, d theta dt. Sine of this angle is right here. Square root of 3 over 2 comes from the x over r. This dx dt is here and here. And then I just simplify all the terms and solve for dx dt, and that gives me the answer. So again, it's exactly the same process. It just looks harder because when you get your equation going, then you have to do a little bit more work to actually get it down into a form where you can solve for the variable that you have. But don't forget, with related rate problems, the secret is drawing a picture, labeling a diagram, writing an equation, taking the derivative of the equation, plugging everything back into that equation, and solving for what you want. If you don't think you have enough info to plug into your equation, go back to your problem and try to figure out if you can solve for those missing pieces to stick into your equation and get you where you're trying to go. And 9 times out of 10, that's going to be exactly everything that you need to do. And there is more than one way to do most of these problems, I'll tell you that. Okay, the last problem in this section is we have an inclined plane, you know, like from physics, an inclined plane. And the slant length of this inclined plane is 20 meters. The vertical height of this inclined plane is 5 meters. A person pushes a box along the ramp at 3 meters per second. How fast does the box rise? How fast does it rise? So basically, you have an inclined plane that goes up like this, like so. So here's my first picture is always usually going to be just drawing exactly what the book has, and then I'll draw another picture usually to label with variables and such. But what I'm given is that this is 5 meters high, and I'm given that this is 20 meters long, along the ramp. And I'm given that there's some box on here that's being pushed, in this direction. And I'm given that this is 3 meters per second. So it's being pushed up the ramp at 3 meters per second. So what I want to know is how fast does the box go up? There's plenty of ways to solve this problem. But in terms of related rates, let's go ahead and solve it in terms of how you would do it with related rates. Well, what we want to know, let's go ahead and redraw this guy in terms of some variables. Right? So it's slightly squishy looking guy there, but it's the same kind of deal. Well, if we start at the end of the plane here, as we push it up, then as time goes on, we're going to be pushing in this direction, we're going to be pushing up, and of course we're going to be, composite motion is going to be along this guy. But at any given moment in time, let's say the box is right here. Let's say it's right here at this moment in time. Then basically you can draw a dotted line right here and say that this distance that I have traveled horizontally is called x. This distance that I've traveled vertically is called y. And this distance that I've traveled sort of along the guy is r. So that's sort of our labeling. That's sort of step 2 we talked about. Let's label things ourselves. Okay? So when we do that, that allows us to take the problem and translate it from being just some numbers to calculus. The other thing is there's an angle here that's being made between the x and the y guys. So when we do this, what we're trying to find, or what we know I should say, is dr dt is given to us as 3 meters per second. See, in the problem it just says, hey, you're pushing it up the ramp at 3 meters per second. But when you label it, you say, well, this is the r direction, so therefore the speed in this direction must be dr dt. It must be equal to 3. So that's given to us. What I'm trying to find is how fast does it rise. Now that I have the guy labeled, I can say, well, this is what I'm trying to find. How fast does it go in the up direction like this? Okay? So the next thing I need to do is try to find an equation that I can write that will express some of these variables. And there's, like I said, there's many, many ways to do it, but this is the way I choose to do it. What I'm going to do is look at this angle, and I'm going to say sine of this angle is equal to opposite over adjacent, which is y over r. Y over r. Now you might think that's not a very smart way to go because you've introduced the angle theta here. But the plus side is that I have y involved. I'm trying to find dy dt, and I have r involved, and I already know dr dt. So I know ultimately when I take a derivative, I'm going to get dy dt in this equation, and I'm going to get dr dt in this equation, both of which either I know or I'm trying to find. So that's the direction I want to go. The side effect of it is that I had to introduce theta to get it, right? But that's easily solvable because when you look back at your original problem, you're given the total length of the ramp and the total height of the ramp. This allows you to define theta concretely. They don't give it to you, they expect you to figure it out yourself. So when you look back at your original guy, what is theta? Sine of theta is equal to opposite over hypotenuse. So it would be 5 over 20. Which is 1/4. Sine of theta is 1/4. So let's go and use this fact and stick it in here. Sine of theta we just found was equal to 1/4. So we'll just put a 1/4 over here. We don't even need to know the angle. We just know the sine of the angle is 1/4. Y over r. Okay? And just to make it a little bit clear, let's move the r over here and let's move the 4 over here. So we'll have r is equal to 4y. So we have got an extremely simple equation here. We just move the r over here and the 4 over here. Let's take the derivative of both sides. Take the derivative of this, you'll get dr dt. When I say take the derivative, we're taking it with respect to time because that's where we're trying to go. On the right-hand side, we'll get 4 dy dt. Okay? And everything we're trying to find here, we have. We know what dr dt is. So it's 3. We stick it into here. 3 is equal to 4 dy dt. So dy dt is equal to 3/4. Just divide by 4, 3/4. And what unit are we talking about? Well, the original block was going up at 3 meters per second, so this is meters per second. Meters per second. And like I say, there are many ways to solve this problem. This is the way I'm choosing to solve it for you to kind of give you some experience. Basically, you label x, y, and r. You tie your variables to what you are given, right? And then you write an equation relating these guys together. Here's the thing. I could have gone and taken a derivative of both sides right here. I would have gotten into trouble because I would have had d theta dt and maybe some other stuff that were... It's possible to go that direction and all. It's just that ahead of time I realized I don't really know much about theta yet, but I'm going to go find it from the problem. Sine of theta is 5/20. That's why they gave you the lengths of the ramps there. So, because when you think about it, the length of the ramp doesn't really matter as far as how fast it's rising. I mean, the ramp could be 100 miles long. The height, the rate of change and how fast you're rising doesn't really depend on how long the ramp is. The reason they gave it to you is, the reason we gave it to you is so that you could actually calculate what this angle is. So we take it, we stick it in here, we solve, we get this equation, take the derivative of both sides, and then you just plug in what you know and get the answer. So, we're done with this section. Done 3 more good related rate problems. They're tricky sometimes because you think you're going down the wrong path. You get an equation, you take a derivative, you're maybe unsure if you're doing that right, you get the answer, then you don't quite see how you can plug everything in to get what you're trying to get. The only way to do it and the only way to get good at it is to practice it. So we give you some extra problems here. What we're going to do is stop this lesson now, let you work these problems, let you digest them, let you get comfortable with them. The next section we're going to work our final batch of related rate problems. And just sort of culminate with those just to give you extra practice and with this tough topic, because a lot of students really do have a hard time with it. The only way you can overcome it is by seeing a lot of examples, rolling up your sleeves and working them. I encourage you to work all of these problems here and in the last section and then the section to come to prepare for your exam. It'll, I guarantee you, help you to have that practice